Okay, so today we'll take a look at the EM algorithm. EM is the E and M stand for expectation and maximization, and it's an iterative algorithm, and it's used for kind of identifying structure in kind of it's like clustering, but it allows us to take into account probability distributions. So we're going to look at just kind of a simplified version of the EM algorithm, which will be the EM algorithm for Gaussian mixtures. All right, and so what I'm going to do is I'm going to generate some data from a mixture of 3 multivariate Gaussian distributions. This is, I mean, you could do any kind of mixture that you want, but today we'll do 3 multivariate Gaussian distributions, and this is how we're going to do it. First, we're going to just randomly select a value to represent either cluster 1, 2, or 3. With some probability vector, okay, that adds up to 1. So here, half of the values will come from cluster 1, 30% of the values will come from cluster 2, and 20% of the values will come from cluster 3. Okay, and so we'll just randomly select, and then depending on which cluster that is selected, we're going to generate values from one of these 3 multivariate Gaussian distributions. Okay, so I've got one cluster or one distribution that's centered at 0, 0, and has this variance matrix, and then component 2 is centered at 4, 4, and has this variance matrix. So notice this one has high variance, but the components are independent. Okay, so we're going to get kind of a big circle centered at 0, 0, like a circle of points, and this first component accounts for about half of our data points. Okay, of course it's random, but we would expect something around there. Component 2 is centered at coordinate 4, 4, so in the upper right, and it exhibits its variance is 1, 1, but its covariance is 0.9, so it's going to be highly there's going to be high correlation, okay? And then component 3 is centered at -4, -4. Its variance is a little bit bigger than this one, variance of 2, but it also has negative covariance, so it's going to be facing the other way. Okay. A mixture distribution, we call these, I guess, finite mixture distributions because it's a mixture of a finite number of components, in our case 3. Its overall kind of the mixture model is represented with this. So we'd say the probability of x given theta, and so this will be x is the point that we're talking about that exists in 2-dimensional space. So, you know, all of our normal distributions that we're generating are 2-dimensional normal distributions. So x is a point in 2D space. Given theta, theta is the collection of all the parameters. All the parameters would be all the mu parameters, all the sigma parameters, and the alpha. Okay, so it would be kind of a collection of, I guess, this vector and all of these mu's and all of these sigmas. Okay, so that's what this theta represents, this big theta. All the alpha, okay. So the alpha sub k's are the mixture weights representing the probabilities that x came from component k. So as we saw, you know, the sum of the alphas add up to 1. So alpha is the mixture weights of each component. P sub k are the probability density functions of component k with parameters theta sub k. So in our example that we're using, the P sub k's are the multivariate Gaussian PDFs. It's basically these things, right? It would be the PDF that represents this 2-dimensional multivariate normal distribution. And theta sub k would represent, for us, the mean and the variance of that multivariate Gaussian of component k, right? So for component 1, it's 0, 0. For component 1, the sigma is, this matrix. For component 2, it's this, and so on and so forth. And then, and z sub k is going to be a vector of it's an indicator variable, okay, and it's a vector of zeros and ones. So in our case, only one value is a 1 and everything else is a 0, and that represents the class membership of X. Okay, so because in the mixture distribution, each X that we generate belongs to one of the classes. It either belongs to class 1, 2, or 3, and so its probability, depends on its class membership. So this is how we would represent it, kind of mathematically, and this is a generic representation that can be used for kind of any mixture model, and it's just that in our case, because we're doing a mixture of multivariate Gaussians, P sub k is the multivariate Gaussian PDF, and then the theta sub k's are the mu's and sigmas. Okay, but if you wanted to have a mixture of, say, some other distribution, you can do that, and your P sub k's would be different probability density or probability mass functions, and then your theta sub k would be the whatever parameters are needed to define that particular distribution. So this is a generic representation, but for us, we're doing a mixture of multivariate Gaussians. Sorry. Phone call on my computer. Okay, and so so this is how the generation of the data might look. Okay, so I'll create an alpha vector, and I've got something to represent kind of the mean of component 1, the sigma matrix of component 1, the mean of component 2, sigma matrix of component 2, mean of component 3, sigma matrix of 3, and so on and so forth. And I'm going to collect all of these things in lists, and I will generate the data using multivariate norm, that package, okay, and I'm going to generate 1,000 data points. So X is going to be a matrix with 3 columns here. All right, and basically for I and the number of rows of X, what I'm going to do is I'm going to sample a value 1 through 3. Okay, sample value 1 through 3 using that probability vector alpha. Okay, so I'm using this to kind of sample either the numbers 1, 2, or 3. And then once I have that sampled, I'm going to use the random multivariate normal function to generate one random multivariate normal, and this will generate basically a length 2 vector coming from the multivariate norm, and this multivariate normal will have the mean that's either mean 1, mean 2, or mean 3. It's going to take either component 1, 2, or 3 from this list using means double vector, double bracket k, and it'll use the matrix that's held in this list, sigma double bracket k. Okay, so this is going to generate, this part's going to generate our length 2 vector representing a point from the multivariate normal, and then it will also store in that row also which component it came from. Okay, so we will know which component it came from. Okay, and when you do this, this is what the data looks like. Okay, so um, so this is a mixture of three components. Okay, so we have the center component centered at 0, 0 with a variance of 9, so it's a big kind of a circle here. And then we have a component up at centered at 4, 4 with the high covariance. Okay, and then we also have the component centered at -4, -4, and a loose and some negative covariance. Okay, and there's a blob of points here, and it's kind of hard. This is the data clusters are not labeled, and someone tells you search for 3 clusters here. It might not be completely obvious what the clusters are. Okay, and you know, if I point to a point here, or let's say I point to a point here, okay, it's a question of, does this point belong to this cluster, or does it belong to kind of the central cluster? Okay, what about this point right here? Does this point right here belong to this cluster, or does it belong to the central cluster? All right. And if we were to just try to use k-means clustering would not do a good job. K-means clustering uses Euclidean distance as the only measure of similarity. Okay, and so according to Euclidean distance, if let's say we put a centroid right here, okay, like that seems like a reasonable spot to put a centroid. Okay, Euclidean distance basically says this point over here is more belongs to this cluster more than this point over here. Okay, because this point over here has a, you know, basically, or this point over here. Let's go with this point right here. Okay, this point right here, its distance from the centroid is further than the distance to this point. Okay, and so k-means clustering, which uses only Euclidean distance, will say this one belongs to this cluster more than this point over here. Okay, and I think we would disagree, right? We would look at this, and seeing the shape of this cluster, we would say, you know, this point is unlikely to belong to this cluster, but this point is likely to belong to this cluster. Okay. Also, you know, if you're using Euclidean distance, okay, yeah, I guess I could have run k-means clustering just to kind of show you, but you know, this point out here, you know, if we have a centroid right here in the middle and a centroid right here, this point right here is gonna be more likely to be associated with this cluster. Okay, although looking at kind of the distribution spread, we might want to say, you know what, this point actually maybe it should belong to kind of the central cluster, because the central cluster just has so much spread, right? So, you know, the data comes in completely unlabeled. This is how we would see the data. And we could tell the EM algorithm, you know, search for like 3 clusters here, okay? And, okay, I guess this point was generated from that upper cluster here. So this is the points that are labeled, because we generated the data ourselves, so we are able to see the labeled data ourselves. Okay, and so we can definitely see that, you know, this point right here does not belong to the red cluster. Okay, and within the red cluster, we have a mix of points from the black cluster. Okay, and down here, this is the data that was generated, and these points belong to the green cluster, and again, these are mixed and things like that. And we want to see, you know, can our algorithm identify these clusters? Okay, and the important thing is that we want to be able to kind of take into account the fact that the clusters could have different variances, okay? And that we're not using Euclidean distance, which kind of effectively says, you know, whichever one is the closest point, that's the one that we're going to use. We don't want to kind of restrict ourselves in that way. We want to be able to take into account kind of a probability function here. So you know, an argument for using the EM algorithm or something would be, you know, this point right here, which cluster should this point belong to, okay? And again, does it belong to the red cluster? Does it belong to the black cluster, the central cluster, or this cluster up here? You know, and the answer is, you know, why can't it belong to both, right? So, you know, when it was generated, it certainly only came from one cluster, okay? When it was generated, each point was, you know, came from a cluster, and we mixed these different points together. But when we assign them to a cluster, we might want to give ourselves a little bit of flexibility and say that we might want to assign them to have a probabilistic assignment here. Okay, so this is what we are going to do in the EM algorithm. Okay, so rather than strictly assigning a point to one cluster, which is what we do in k-means clustering. Okay, so in k-means clustering, we just say, here's the centroid, here's the point, which centroid is the closest. Okay, and that's the same rule that applies also in like kernelized k-means clustering. We just say, you know, here's the centroid, which one is the nearest one, and we assign it to that centroid. Okay. Instead, what we're going to do is we're going to use a Bayes classifier. Okay, so you know, we learned the Bayes classifier a couple weeks ago, and that creates probabilistic assignments, right? So we're going to say, here are maybe like 3 clusters, and this point right here, this new point, it has a 80% probability of belonging to this cluster, 19% probability of belonging to this cluster, and a 1% probability of belonging to this third cluster. Okay, and so and we would create that, and we call that a membership weight. Okay, and so each point gets a vector of membership weights that the membership weights add up to 1, but they are probabilistic assignments. So it is possible for this point to belong to, quote unquote, belong to more than one cluster, but it does so probabilistically. Okay, so we're going to say this one is 80% cluster 1, 19% cluster 2, 1% cluster 3, or something like that. Okay, so again, rather than a direct, this point definitely belongs to this cluster, we do a probabilistic assignment. Okay, and there's a lot of similarities between k-means clustering. Okay, and so in k-means clustering, you assign the points, and then once you assign the points, you recalculate the centroids. Okay, with the EM algorithm, once you assign the points using the membership weights, you're going to calculate the parameters of each cluster. Okay, and in our case, the clusters come from these multivariate distributions. So we're going to calculate the mean of each distribution and the variance matrix, the variance covariance matrix of each distribution, and they are going to be weighted means and weighted variance covariance matrices. Okay, and we're going to use the membership weights of the points in the clusters. Okay, and what that does is it maximizes the likelihood of the values that are, quote, assigned to the cluster, right? So and we do this and we iterate back and forth. Okay, so you can kind of think of this EM algorithm as a bit of a blend between k-means clustering, but using and a Bayes classifier. Okay, so k-means clustering, you assign points to the nearest centroid, the cluster with the nearest centroid. Using the points that are assigned to that cluster, you recalculate the centroids. With the EM algorithm, you assign points probabilistically to all of the clusters using the Bayes classifier. And once you have those assignments, then you recalculate the mean and variances, okay? And they're going to be weighted means and weighted variances. So, so I'll show you kind of the equations for this, okay? So the membership weights are calculated using the Bayes classifier, all right? And so, so these membership weights is going to be basically the probability that point I belongs to cluster K, all right? So to say point I belongs to cluster K is designated, is basically the probability that Zik is equal to 1, and basically Zi everything else is 0, okay? Given basically the value in xi and all of the theta parameters, okay? We're going to say this is, Bayes rule, likelihood times prior divided by the marginal, okay? So the likelihood is basically our probability density, right? So this is the multivariate Gaussian PDF, and we're asking, what's the probability density function of getting this particular x value if it comes from component K with mean, with whatever mean and whatever theta we have specified, okay? So we do that. And then we're going to multiply that by alpha sub k, which is going to be our prior probabilities, okay? And we're going to divide by the marginal. The marginal probability is, like we've said many times with the Bayes classifier. The Bayes classifier, the marginal probability on the denominator is the sum of the numerator across all possible clusters. Okay, so we're going to take the numerator and calculate it across all possible clusters and add them up. All right, so the alpha sub k's, okay, these are the prior probabilities, okay? So these are the prior probabilities from the previous iteration that a point belongs to cluster K, okay? And so this is going to basically be the proportion of points that are assigned to cluster K, right? And I put points that are assigned in quotes because points are not truly assigned, okay? Points are not truly assigned. So, but it's basically the number of points that are assigned to K divided by the total number of points. However, this number of points that are assigned, okay, number of points that are assigned, it's not an integer, okay? So it's not like out of 1,000 points, 450 points are assigned to cluster K, okay? It's not going to be necessarily an integer like 450. It's the sum of the membership weights. So it might be you have 400 points with a 99.9% probability of belonging to cluster K, okay? And so you'd have, 400 times 0.999, which would add up to 396, I think, or something, okay? And then, maybe this point has a 30% probability of belonging to the cluster. And so that the ending number could end up being some non-integer like 452.7, okay? And you would do 452.7 divided by the total number of points, n, okay? So it's the sum of the membership weights, which again, is found using the Bayes classifier, and it's not the actual number of points. It's the sum of the membership weights, which, I guess intuitively, you can kind of think of it as the number of points that are assigned to this cluster, but again, it's not really an actual count of numbers, okay? So you can't count this, it's the sum of the weights. I hope, is this okay? Let me know if you're following along, or if you've got questions, or if this doesn't make any sense at all. Just you can give me some feedback as things are going along here. Okay. So that is the membership weights. I'm sorry, that's the alpha part here. Okay, and then this the p, okay, p sub k. Again, this is just coming from the multivariate normal density. All right, this is just the PDF of the multivariate normal distribution. This is the full PDF. We don't actually have to use this. We can just use the density function, the d, d for the multivariate normal, and we would use give it the new x value, whatever x sub I value that we're calculating here, given for x bar and the variance of k, right? So so the probability, we're asking, what's the probability density of getting this particular x if it comes from some particular component with parameters x bar and variance of k. We're going to do that, okay? And we would have to do this basically for each class, right? So we would so if you think back to your Bayes classifier homework, you had to find the likelihood that it some observation belonged to Virginica, or the likelihood that some observation belonged to versicolor, or the likelihood that some observation belonged to setosa. And you did that by asking what's the probability of getting x if it came from this normal distribution, or if it came from this normal distribution, or something like that. Okay. Although in your homework you did the naive Bayes classifier, so you did it as a product of normal distributions, and here we're just going to use the multivariate normal distribution directly. All right, so that's how we would get the W's, right? So we have a way to calculate the numerators. I didn't bother talking about the denominator. The denominator is you calculate the numerator for cluster 1, cluster 2, cluster 3. You calculate the numerators across all the clusters, and then you sum them up, right? Okay, and now for the M step, so that's the E step. You find these weights here. The M step is recalculating the parameters of each cluster. Okay, so this would be equivalent to recalculating the centroids of your clusters in k-means clustering. Okay, here we're recalculating the parameters of each cluster. So each cluster has a mean and a variance. So we need a way to find the recalculate the mean, which would kind of be the equivalent of the centroid. All right, and so we do that by basically taking the weighted mean. So we're going to take each x, and we're going to multiply each x by its weight, by its membership weight, right? So x values that are have a high probability assignment, okay, of belonging to a particular cluster, right? Their membership weights are going to be basically very close to 1, and they're going to contribute a lot towards the mean, okay? X values that are unlikely to belong to a certain cluster, its membership weight is going to be close to 0, right? And so it will, we're going to add basically, you're basically not adding that point in if the membership weight is very close to 0, so you're almost like not adding that into the sum, okay? And then again, you're dividing by n sub k, which is the kind of the quote unquote number of points assigned to to cluster K. It's not truly it's not really the number or the count of points, but you're dividing it by the sum of the WIKs. Okay, the weights. So this is pretty much just a weighted mean, right? I think you guys are familiar with the concept of a weighted mean, that you're just weighting certain points more heavily than others, and that's what we're doing. We're just weighting certain points more heavily than others using their Bayes probabilities, right? So we calculated the Bayes probabilities, and we're going to weight some of them more heavily than others, right? And that's how we're going to calculate basically the centroid of each of these clusters. Okay, so we're using a weighted mean for the centroids. And if you look at this is pretty much the same formula we used for calculating the centroid when it was k-means clustering. Okay, except in k-means clustering this was a z, which meant these weights were either 0 or 1. They were I'm drawing a blank. Dichotomous. Okay, it was either a 0 or 1. They were binary. So either the point contributed to the mean or it didn't. Okay, and here we're just allowing the weights not to just be 0 or 1, but to be a value between 0 and 1. And it's kind of now a scale that says this will contribute more or less, not just it does or it does not. This is pretty much the same formula, but it's weighted. Okay. All right. So that's going to give us the centroid. All right. And now we calculate the variance covariance matrix. Okay. So if I said just give me the variance covariance matrix of your x values, okay, it would be basically this. If we removed this weight value, right? If we remove this weight value, this whole thing would give us how you could calculate the variance, right? Using kind of vector notation, this would be how you could calculate the variance, right? You just do x minus mu quantity squared, basically, all right? But in matrix notation, x minus mu times x minus mu, and we're going to divide it by 1 over n sub k. This, technically, the regular variance would be 1 over n minus 1. Here we're going to go for the MLE, so it's just going to be 1 over n sub k. So again, this is the weighted number of points that are assigned using the weights. And then here we're basically going to take each x, and we're taking these, basically it's squared distance from mu. Okay, we're going to do x minus mu, basically squared, but it's a matrix, right? X minus mu times x minus mu k transpose, and we're going to multiply it by a weight. Okay, so some of these will have heavier weights and will contribute more towards the total sigma matrix, and others will have lower weights and will contribute less to the sigma matrix, right? So it's kind of like a weighted variance, right? And so that recalculates the variance matrix here, right? So we have a way to calculate the centroid, or the mean and the variance, okay, the equivalent of a centroid and the variance thing, and we use those, okay, going back when we calculate, because we're going to iterate back and forth between the E step and the M steps, right? So again, much like k-means clustering, where you reassign points and then you recalculate the centroids, we're just adding more flexibility here, okay? We recalculate the centroid and now the variance, because it's coming from a Gaussian distribution. We recalculate the mean and the variance using the weights, and then we recalculate the assignments probabilistically, and they end up with probabilistic weights. Here. All right, and that's pretty much the EM algorithm. I've posted a little bit of notes from from another school that I think did a good job of explaining the EM algorithm, and I'll also post up these notes. And now I'll just kind of demo them. I hope you guys are following along. Let me know if you're not, and let me give you the first quiz answer. First quiz answer today is B. Also, I think on Wednesday was also, first one was B, and today it's also B. First quiz answer is B, as in bear. Okay, so here we go. So the clusters are not labeled. This is how we're going to see it, right? And these are the true group assignments. These are the true group assignments. And what we're going to do is we're going to just kind of mess around, okay? And so I'm going to just start off and just arbitrarily basically say a third of our points come from cluster 1, a third of our points come from cluster 2, and a third, maybe a slightly more than a third of the points, right? So 0.33, 0.33, and 0.34, these will be our distribution, initial distribution. And here, I'm going to start off with a mean at 0, 0, a mean at -9, -9, and a mean at 9, 9. And I'm going to start them all off with variance covariance matrices that are basically equivalent to the identity matrix, okay? I've intentionally hidden the rest of my code because I'm going to give this to you as a homework assignment for you to work through as well, okay? All right, so this is kind of where they initially start. We start off with a centroid down here, and a centroid up here, and a centroid right here, and then and we use a Bayes classifier to say, all right, which points belong to which cluster, and and so what it does is it this is how it does the assignments, okay? This picture is a tiny bit misleading, okay? Because when I color a point on in R, I'm only able to kind of basically color it one color, right? This point is either going to get colored black or it's going to get colored red, okay? But technically, everything here gets a probabilistic assignment. So all of these things are kind of like on the border. Like this one is probably something like 51% red, 49% black, okay? And then this one over here is probably 49% red and 51% black, okay? But when I color them, I kind of just have to say, all right, which one is the highest value? And let's cluster it that way, right? Kind of like when you did your Bayes classifier in your homework. I think that's what you guys ended up doing, right? You got your probabilistic assignments, and then you just said which one's the biggest, right? Which one's the biggest? That's going to be kind of your classification. Sorry, you got your class assignments, class probabilities using the Bayes classifier, and you just said which one's the highest. That one is the one that we assign it to. Okay, so that's how I'm coloring the points. I'm just saying which one has the highest cluster probability, and I've colored it that way. But all of these things that are kind of like borderline red and black, they're truly it's a mixed probability, right? It's probably 49% red, 51% black, or 51% red, 49% black. I just can't represent that using the colors, okay? So I think I've written all of this right here, okay? These circles represent kind of the initial variance covariance. Like if I were to draw the contour plot of the multivariate Gaussian with the identity matrix, and they would be kind of these circles, and obviously this would be a terrible thing, okay? So then what happens in the next slide, okay, is what you're going to see is so it's kind of, I didn't separate the iterations. Maybe I should have, okay? But basically, I will recalculate the centroid using the weighted mean of basically all the points that, or basically all the weights that go towards green, right? So, so this one is probably like 100% green, and these ones are probably like 51% green, and these ones are 49% green. Okay, they're class probabilities, and so I recalculate the centroid of the greens, and this ends up being kind of the centroid here. Right. We also calculate the variance covariance matrix of all the points that are quote unquote assigned to green. Again, taking into account that they are probabilistic assignments, and so it's going to include some of these points that are colored black, but have like 48% membership to green, or 40 or 30% membership to green. They still get counted, just at a lower weight. Okay, and so this ends up being kind of the assignment there. And then we do the same thing with the reds, and we can see because of the covariance that appears here, the shape of the thing reflects that, right? All of these points that are currently assigned to black have a huge amount of variance. So when we recalculate the variance matrix, it gets reflected as such with kind of this huge blob here. Okay, and then we continue this, and we update this, and we say, all right, we'll recalculate the variance that of these points that are now probabilistically assigned to green, recalculate the variance covariance matrix of the points that are probabilistically assigned to red. And again, keeping in mind that it's not just these ones only are assigned to green, they are probabilistically, and so some of these points that are green, have these points that are colored green are, have probably mixed memberships between green and black, and these ones have mixed memberships between black and green, and these ones are probably mixed between red and black, and so on and so forth. And we kind of iterate this, and so now it fits the data like so, and we can see that as these points get concentrated, as I iterate, this is kind of, after several iterations, these are the probabilistic assignments. Okay, so oops. So we started off here, and then as the algorithm progresses iteratively, it improves the assignments as such. Okay, and if I allow this, again, it's iterative, and I didn't plot every single iteration. Well, this is stepwise, but I'll just allow it to continue to run, and after several more iterations, these are kind of the final cluster assignments that are found by the algorithm. Okay, and so probabilistically, these points get probabilistically assigned to red, and these points get probabilistically assigned to green. But again, these points, this is probably something like 51% green and 49% black, and 49% green, 51% black, or something like that. But again, when I color them, they just show up like this. Okay, so these are kind of the final results of allowing the EM algorithm to run for a long time, and we can compare that to what were the original true group assignments. Okay, and we see it does a pretty good job, right? You lose the kind of the nuance, right? So in the true groups, the points that were down here, some of them belonged to the black cluster, right? And here they all just kind of get clustered in with the red cluster, because there's no way to tell, which of these points belong to the central black cluster. And again, again, the cluster labels are arbitrary. So this one called this one green, and this one called this one red, but this is red and this is green. It doesn't matter. It's just these are kind of your different clusters, and it identified these as such. Okay, you can start with different starting locations, and sometimes it works and sometimes it doesn't, right? Sometimes, so here I'm going to start with these starting locations, okay? And you can just see with these starting locations, it just kind of, because they're equidistant, you know, the borders kind of get drawn straight and flat, and just because there's a little bit more of a concentration of points, the mean is going to get drawn a little bit closer towards the concentration of points. So in the next iteration, it automatically just the centroid ends up over here. The centroid ends up for the green ends up over here. And again, trying to take into account the variance to accommodate all of this. This is kind of the shape that it ends up getting, and then as it runs, it ends up finding the clusters again as well. Okay, so it's pretty interesting to see the EM algorithm work. And again, the advantage of the EM algorithm in all of this is that you can specify different variance covariances. So it's not just using Euclidean distance as your measure of similarity. And so we can say, you know, this point over here, it's technically closer to the centroid than this point. But probabilistically, because we are able to take into account the variance covariance matrix, we can say this point is very unlikely to belong to this cluster, okay, because of the way our multivariate Gaussian distribution is drawn. Okay. If I started off with some really bad starting weights, it's possible that it doesn't find the correct clusters as well. Okay, so the EM algorithm is not error-proof, or you know, and again, you know, everything is a probabilistic assignment, and I can just let this continue running, and these are going to be the final groups identified by EM, and that ends up being fairly similar to the true groups that we had. I don't know how many slides ago it was. So these are the true groups, and if I scroll down to the last page, it does a fairly good job. Okay, and again, in the true group assignments, this is a mix of green and black, and you know, down at the end, we're going to get, these are all probabilistically assigned to green again, but you know, they are going to be you know, mixed weight between green and black. It's just as far as coloring them on the plot, we're just saying which one has the highest probability here. Okay, and again, and you see these points that are way out here. Technically, as far as distance to the centroid, this point is much closer to this centroid than it is to this centroid. Okay, and so k-means clustering would definitely assign this point to this cluster, but using the EM algorithm, because we're able to take into account the variance, we can say this middle cluster in the has a huge variance, and so it's more likely to come from this middle one, which rather than the green cluster, which has a variance that's not as big. Okay, that's it for today. Have a good weekend, a good Memorial Day weekend, and I will post up your next assignment, which covers clustering. And and the second quiz answer for today is A as in apple. A as in apple is your second quiz answer. You can, so I'll post up the next homework assignment. I'll probably put that up in week 9. That will be homework 5. Is there a score associated with EM like k-means? Off the top of my head, there is there's something. It's like a lower bound of something, but I don't know off the top of my head, so sorry. Right. Yeah, I know what you're talking about, but yeah, I don't know one off the top of my head. Again, this is, again, it's an unsupervised learning method in that you just kind of say, you know, we're looking for this many kind of mixtures or this many components, mixtures of this many components, but I'll have to get back to you regarding if there's a score here, okay? But you can kind of think of the EM a little bit as a, you know, again, a blend between k-means clustering and Bayesian classification for the probabilistic assignments, and it takes into account kind of the variance covariance matrix of the Gaussian mixtures, or the Gaussian distributions. Okay, that's it for today. Have a good weekend, and we will see you on Wednesday. All right, so we'll see you guys on Wednesday.